Yeah, good morning to all of you. So today we are going to discuss finite fields. It is completely new, so you don't worry about what happened in the previous classes, right? Okay. So for that finite fields, the topic is finite fields. So for that, first we need to know what is a field, right? So you all know what is a field, right? Field has two binary operations plus dot, right? So it is a, yeah. So somebody tell me definition fast if it is okay. Otherwise, I'll tell it. F plus dot is a field. Yes. Yeah. If F plus is an abelian group, right? Is an abelian group.
Sir, the screen is getting blocked.
Here also. Okay.
Yes, sir.
Okay, fine. Yeah, that's what I'm about to ask actually. Now?
Now it's fine.
Now it's fine. Okay. Is an abelian group. So F plus is an abelian group, and then this F multiplication, right? F minus 0. If I remove 0 from the F field F, so F minus 0, so multiplication is also an abelian group. Okay, and what next? Distributive loss, right? Distributive loss hold. But actually, since it is commutative, one distributive law is sufficient, but in general, it total. So here, including closure property, okay, plus is an abelian group, plus is a binary operation. So binary, if you include that also, then total 5 conditions are there: closure, associativity, identity, inverse, and commutativity. Here also 5. Here 2. Total 12 operations. But as I told you, one distributive law is sufficient. So very large number of operations, right? Yeah. So this is what a field is, right? But before that, just I will try to inform you. So just recall you so that so for example you have uh, so for example you have rings are very big, right? These are rings. In the rings we have another set, right? That is commutative rings. Commutative rings. Okay, every commutative ring is a ring, but ring is not commutative, right? Yeah. So now commutative rings. Then we have another one called commutative rings with unity, right? So this is a commutative ring with unity. So all these operations are with respect to multiplication. Ring already group with respect to plus abelian group. So only with respect to multiplication, we only have few things. What are those things? Associative property and distributive loss with combining those two. But commutative means commutative with respect to multiplication. Commutative ring with unity means commutative ring with respect to multiplication, and identity is also there with respect to multiplication. Everything is with respect to multiplication. Then we have integral domain. So my feeling is that why I'm telling this, for me integral domain means that it is a commutative ring with unity and cancellation loss hold, ID. Yeah? So it is ID means for me it is commutative also. Some textbooks will not say, right? That's why I'm telling you a priori with unity plus without zero divisors. Okay, zero is the only zero divisor. Some people say that zero in the definition they'll exclude non-zero element only zero divisor, but I'm including zero is the only zero divisor. Okay, otherwise cancellation loss hold. Otherwise, zero is the only prime ideal. So there are various ways to define integral domain, right? Yeah. So next thing is that so in integral domain, then we have UFDs, right? What are UFDs? Unifactorization domain. So there every element can be written as product of irreducible elements uniquely up to associates, right? Then it contains PIDs. What is PIDs? Principal ideal domain. There every ideal is generated by single element, right? Now this contains EDs. What are EDs? Euclidean domain.
Sir,
Ah, yes.
UFD should be inside PFD, right?
UFD should be inside.
Inside PID.
No, no. PIDs are larger. Every PID is actually UFD. I'll write below, okay? And later inside we have fields. I'll write now. I'll give examples also so that it will be easy for you. So what is that I'm saying is that first is the field. Field is the smallest. Field contained in Euclidean domains. Euclidean domain contained in PIDs. PIDs are contained in UFDs. UFDs are contained in IDs. IDs are contained in between many other things are there. Okay, I'm not going into them. IDs are contained in commutative rings with unity. Okay, and contained in rings. Okay, I'm not writing commutative rings now. So, so you know that ZX is
It's a UFD, but not a PID.
so it is UFD but not PID. So this is example here. So for example, what is ID but not UFD?
Z root -5.
Okay, good. Z root of -5. It is ID but not UFD, correct? So what is a commutator ring with unity but not ID? If you know.
On matrices. But it's not commutative.
It is not commutator, right?
Uh,
Yeah, ZNs, right?
ZN.
Zn is a commutator ring with unity, but it is not, when n is not a prime, n is composite. That also we need to tell. So that is the main idea here today. Actually, we are looking at this. If n is composite, then Zn has zero divisors, right? So it is not ID. Yeah. So there are PIDs but not ED. Okay. That is Z of 1 minus root of minus 19 by 2. So this is a PID but not ED. Okay. There is a ED but not field. What is that? Integers, right? Or fx. F is a field, then fx. So I wrote these examples. I hope it is clear. This is this guy but not this. Then integers automatically Euclidean domain, principal ideal domain, UFT, and ID, then commutator ring with unity, commutator ring and ring, right? Yeah. Is it okay to everyone? Yeah. So I can prove all of these also, but yeah, and that is not our goal. Yeah. So these are the ideas. Now, main thing is that now we are in the fields now. We want to define fields only. So let F be a field. Let F be a field, right? Then we have the concept of, we can define this, right? You know, fx. What is fx? Fx is set of all polynomials, right? So how it is defined? So it is of the form a0 plus a1x plus and so on plus an x power n, right? So here, so these n belong to natural number, right? So n belongs to natural number and a belong to the field f, right? Yeah, and x is indeterminate. X is indeterminate. Yeah, I'm not writing it. So any questions here? See, a belong to f implies as can be 0 also, right? So some people say that you have to take union 0 since a0 is not covered. No, I'm not taking like that, right? So because of this is taking care of that also, a0 can be 0 also, right? See, A's are 0, a1, a2, an are 0, then a0 only comes, right? This a belong to f I wrote. Is it okay? Yeah. So is what do you know about fx? It is a ed, right? So automatically it is PID, everything. Very nice guy. It is almost field, but one thing left, right? So it is a field, then what happens? Okay. Uh, so an ideal I is maximal in fx if and only if, yes.
Is generated by an irreducible polynomial.
So it is generated by any actually any PID. So it is generated by an element. So here I am writing fx, right? So since it is a PID, so see there are two things. Ideal, so ideal is principal, so it is generated by single element. But now maximal, so maximal say that it is irreducible element, right? Yeah. So these are the things. So if and only if it is generated by irreducible polynomial, right? Yeah. Okay. So this is clear. Okay. Let me start saving. Some any problem comes later. Yeah. So in the meantime, just think of that. So what are the irreducible elements and all, right? Yeah. Okay. Yeah. I'll do later then. After some time. Yeah. So so for example, if I take my field is equal to real numbers, right? Okay. So can you tell me irreducible polynomials in Rx or irreducible element in Rx?
X square plus 1.
X square plus 1, right? Right. So we have, but that is not you need to tell. When I ask irreducible polynomial, you need to tell much simpler one.
X plus 1.
Yes, think
X.
much simpler one. X itself, right?
Yes.
So ideal generated by X is maximal ideal, right? Yeah, I already thought that exactly happened. See? Okay, let me save, right? 1 minute. Yeah, is it visible?
Yes, sir.
Okay, thanks. Yeah, sorry, I thought that something will happen. Right, okay. So this is maximal ideal. So why it is maximal? So R by this, why it is maximal? Because R of X by ideal generated by X, this is isomorphic to R, right? So in fact, what happens is that R of X by any polynomial AX plus B, right, is isomorphic to R. So these are all irreducible polynomials, right? So you know that R by I, R is a ring, commutative ring with unity. R by I is field. R by I is field if and only if I is maximal, right? I'm just recalling. Okay, these are not. Don't worry. I will. These are sometimes when I use it. I'm just recalling. Okay, before introducing, I should not use. No, just I'm telling. Yeah. Yeah, so these are like trivial examples, non-trivial examples, as you rightly pointed out, right? This is x square plus 1, right? But one point is that, see, so this is isomorphic to what?
C.
Complex numbers, right? It is isomorphic to complex numbers. We know that. But my interesting point is this. So is it C is isomorphic to R2, R cross R?
No, sir.
But we need to ask isomorphism with respect to what? As a vector spaces. Do you agree?
Yes. As vector spaces, they are identical.
As vector spaces over R, so they are as vector space, they are isomorphic, right? But C has a nice structure. Vector spaces, what is they want? They want that abelian group and extra that scalar multiplication, all those properties, right? But now C has an extra structure. Vector space does not define multiplication among the elements, right? But once, but C has that, R does not have. So now I can equip, I can convert R cross R into a field by putting some operations, right? A comma B plus C plus D, C comma D. So here there is no problem. This is a K already came from the vector space structure. So that is actually A plus C comma B plus D. So this is the way you already know R square is in a vector space over R. So this is not a problem. But now vector space does not have multiplication, right? So now I take this C comma D, right? Now how do you define it now, right? This is a question mark. So if I define AC BD, right, is it forms a field? If my
No, sir.
definition is like that, it is forms a field.
No, sir.
No. Why? What is the problem?
It is not even an integral domain.
It is not an integral domain because 1, 0 and 0, 1 will create problems, right? So that is the reason that we need to define in a different way. Then how do you define? Think this A comma B as A plus IB, C comma D as C plus ID, then multiply whatever you get, right? Now that is AC minus BD comma AD plus BC, right? So if you define this way, then it becomes a field. So this definition coming from this complex number somehow, right? So this is one of the nice area at that time. So you know Hamilton tried to show that R cube also has, R cube also can become field with respect to some multiplication that we may not able to see. He tried, but later he proved that it is not possible, right? Then at the process, in the process, he introduced R power 4 isomorphic to Hamiltonian group, right? A plus B, I plus C, J plus T, K, right? And he defines some operations, and it is a first example of nice example of division ring, but not a field, right? I'm just telling you, recalling certain things, right? With I multiplied to J multiplied to K, yeah. So this operation, so but it is not commutative. So he defined that he able to go up to division ring. But up to field, these are the only field, R2 only field. I can bring some structure in R2 so that it became a field, right? Yeah. So, okay, why I'm telling these things, right? I'm telling these things because now you see that R of x by x square minus 1, x square plus 1 is isomorphic to C as, right? It is actually equal to C, isomorphic to C, and R of x by x square plus 2, where it is isomorphic to?
R adjoin root to I.
But is it not isomorphic to C?
Yes, it is.
Because it is a field, right? And what is the its extension, right? Yeah, so it is also a field. So and how modulo. So here how elements look like, right? This is R by I, R by I, R by I elements looks like x plus I, such that x belong to R, right? So here you know the definition of how do you multiply, add, and all, right? But when I'm doing this in this particular example R of x, then how element look like, right? R of x by x square plus 2, right? So here how element look like. They are again polynomials, but I'm quotienting here. As R of x is indeterminate. Matlab x is free. It does not satisfy any relation, right? But this is equal to what? A0 plus A1x, right? But A0, A1 belong to R, loosely speaking, right? Because now we are quotienting. When you, whatever the polynomial you take here, I am dividing it with and some conditions. So as a structure, it is a complete different structure. Now multiplication is also a little different in compared to that. But no one discussed those earlier, but don't worry. So this is what I want to convey. So clearly, It is a vector space over R of with dimension 2, but then it is isomorphic to complex numbers. But this is a field. Here also multiplication is there, but now that multiplication is little different from complex numbers also. Okay. Okay. So you may know one person called Kronecker, right? So Kronecker asked these questions. I have a field here. I have a field here, right? And then I can consider this. Then I take a irreducible polynomial, like fx equal to, so an x power n plus an minus 1, x power n minus 1, and so on, plus a0 is irreducible in fx. So it is complete. F is abstract now. We don't know. When I say R, then you know what are these, right? But now we do not know what is this f and what is this polynomial also. But I told that it is irreducible, right? Then he told that there exists a field, very abstract, and that completely changed the scenario. There exists a field, okay, such that there exists a field K, such that, so F is contained in K, and K contains root of fx. Are you following this point? Are you following what I'm saying?
Yes, sir.
So this is, I'm without proof, I'm telling this. This fact is very useful. Kronecker actually, this result actually revolutionized. This is very, very important result. Okay. What is that he done? So he just modulo this polynomial, right? Ideal generated by this. And that is a field. And what is the root for that polynomial in that field? That x itself, right? X satisfy that, right? And then, so like that he brought it. Yeah. So that is the idea. So for example, you able to see, right, x square plus 1. R of x does not contain the root of x square plus 1, right? But I can go to a field, a bigger field, where this contains a root. But this is now, see, we know, but in general, we do not know, right? So we quotient it, then I know this is a field first because of the properties of PIDs and all, right? So that field, now this is a field, and here x is a root for this. Okay, that x is here, it is I. We'll call that later. We denoted that root of x square plus 1 as I. Then we created a new system called complex numbers. Right? Yeah. Okay, so this is one thing. Without proof, I am telling this. What Kronecker told, that there exists a field which contains k, and the k contains the root of x. So this much assumption only I am taking in this course now, in this class. Yeah, right. And another aspect, we proved in the previous course, right? You are all there. Let F be a field. I'm recalling that. Let F be a field. Okay. And fx belong to fx of degree n. Right? Then F contains, yeah, can you complete? I think you may reading my mind. F contains at most
N roots.
at most n roots of f. So you take any field and it belong to that, then f contains at most n roots of f. You remember that we proved in the primitive roots, right? Primitive roots. Yeah. So there we need it actually in order to show that this UP is cyclic. Yeah. So we need this theorem and we proved. Actually, people struggle to show that UP, you remember? All the numbers which are relatively prime to P. So that is cyclic we proved. We proved that UN is cyclic when n is equal to 2, 4, right? Prime numbers, P power K, 2 into p power k, where p is an odd prime, right? So while proving it, we need to show people struggle to prove them there actually. So Lagrange proved this result. Lagrange, after that only people able to prove that UP is cyclic, UP power k cyclic and R. Right? In particular, UP cyclic. Yeah, right, good. So this also I'm not proving, we proved, but proof very simple for this, we'll prove by induction, right? If I take a polynomial, linear polynomial, ax plus b, right? Then automatically it has a root in fx, right? In f, right? Why? What is the root of this polynomial? Minus b by a. And already when I'm telling degree 1, already a not equal to 0. Since a field, so b minus b by a will belong to that. So it has a root and exactly one root done. Now we go to the higher. So now prove by induction. So for example, I have a polynomial of degree k. Assume that all polynomials of degree k has at most k roots in f. Now I take a polynomial of degree k. Now I want to claim that it has at most k roots. Okay. If there are no roots, we are done. If it has a root, then that f x minus alpha is the root. Alpha is the root. Then x minus alpha divides the polynomial. Then my fx can be written as x minus alpha into polynomial of degree k minus k. But by induction, that has n more n roots. So total n plus n k roots, right? Sorry, I'm using n k. Yeah. So proof, I hope clear, and recall the entire proof also. That is by induction, right? So this is done. Good. Now I'm going to the one more last thing. Preliminary is required. I will introduce, then we'll move forward, right? So what is that I want to introduce is that characteristic. Okay, characteristic of R. You know it, but characteristic of ring R. Okay, what is the characteristic of R?
Zero.
Do you know anyone of you?
Zero.
No. That it is not like that. Characteristic of a ring is the smallest positive integer definition. Smallest positive integer n such that n into a is equal to 0 for every a belong to R, right? If exists, else otherwise 0, defined as 0. It is definition. If you are able to find a natural number n such that n into a equal to 0 for every a, then we'll say that characteristic of R equal to n, right? Otherwise it is 0. If there is no, you do not able to find any natural number, so that n into a equal to 0. Okay. What do you mean by n into a here? So I'll tell that also. So you have a ring, okay, and you have a set of integers is a ring, right? Then I can define a map from set of integers to R. Okay. So what is the definition? Make. Okay, R is a ring. So with respect to addition, it has a abelian group. So addition is there, right? So I'll map n to, right?
N times f of 1.
So I'm assuming that R is a commutator ring with unity.
N. N dot 1 or whatever.
N dot 1, very good. Yeah, since I do not know elements in R where I can map, right? But I know here I am taking integer and I'll going to map to n dot 1. But what is n dot 1 means, right? N dot 1 means 1 plus like that 1 times, right? So see, we remember this n is not an element in R. I cannot multiply. Even though R is a ring, it has the multiplication, but this is not an element of R. Okay. If you know module, then it is actually every abelian group is a module over Z. That is actually here. But don't worry, you do not know module. Don't worry about that. right? Okay. So yeah, so this is the way we do, right? N into 1, right? So it is going to one of the elements here. Okay. So now, um, so it can be 1 1, right? You can easily check that it is a homomorphism, right? It is a homomorphism. So if f is 1 1, then what happens? The kernel of f is equal to 0 alone, right? In that case, we say that the characteristic of R is 0, right? So for example, I take my this, right, Z2, so Z6, for understand, right? Now, now what is going to happen? What is the kernel now under this map? And going to n dot 1, right? Yeah. So now can you tell me what is the kernel of F? Yes.
Ideally generated by 6.
Yeah. So ideally generated by 6. Since it is a here, so it is equal to 6 Z, right? So now what is the characteristic of Z6? 6, right? So characteristic of Z6 is 6 only. So in general, characteristic of Zn is n, right? Yeah. Okay. So you understand this. Now you know famous theorem. You know this, but today we'll prove that little faster way. Can you expect what is that I'm going to state? I think you can predict.
Characteristic of field is a prime number.
Yeah, but I'll prove much bigger version. What is that?
The cardinality of finite fields.
No, 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 no. So I know that today I'm doing finite fields and all, but characteristic of a field ke alawa I'll do much better. Let R be a an integral
Characteristic is
domain.
either 0 or a prime.
Integral domain के लिए I'm doing for directly for integral domain. Yes, 0 or prime.
It
Correct.
is the
Not
kernel
only
of
that,
the.
I'm saying that it is not only for fields. I'm proving directly for integral domains because every field is an integral domain. So something is available for integral domains. Why can't I use it, right? Yeah. Let R be an integral domain. Yeah. Then full stop. Then the characteristic of R is either 0 or prime. Directly I'm attacking the integral domains. Okay. Now I'll try to prove this. Right? Proof. So whenever you come across, okay, I told you earlier, whenever you come across something to prove either R, P or Q, so how do you proceed, right? Suppose characteristic of R is equal to 0, right? Then we are done. This is the approach. P or Q, you assume one of them, we are done. So now characteristic of R is not equal to 0, okay? That is, suppose let characteristic of R is equal to n, right? We are assuming characteristic of R equal to n, right? What is a climb? So now climb is n is prime. So I'm just asking all the other students. Okay, today I told you that I will not ask anybody by name. So is it all of you are clear? Can you say? You do not want to speak? Can you tick yes so that everyone is following? Huh? Can you raise yes, please? Till now everything is fine. Pratik, yeah, okay, thank you. Yeah, okay, thanks. Yeah, good. So characteristic of R is prime, right? So n is prime, I need to show. Correct. Okay, now go forward. Yeah, you can tick no. So now we can untick. Okay, how to prove that, right? So we'll prove by contradiction, right? Suppose n is not a prime. Suppose n is not prime. That means n is equal to some r into s, right? But I told that so now there is a contradiction I want to bring, correct? Okay. So, but I know that 0 is equal to 1 into n, right? So this is equal to what? 1 plus 1 plus 1. See, people, even many teachers also does not, they will write directly this r into 1, s into 1. Actually, there is a lot people not realize exactly what is going on. So first we need to write like this. By a distributive and associative property, we can write like this. This here how many ones? R ones. Here how many ones? S ones. Is it clear?
Yes, sir.
Yeah, good. So I'm writing n into 1 only. Yeah. Yeah. So n into 1 is equal to 1 plus 1 plus 1. So it is I write like this. But please be careful. This is actually elements of the ring or integral domain. It is now element in the integral domain, element in the integral domain. Okay, because this n into 1 is n into 1, how it will be in the ring? It is because I'm adding 1 n times, but 1 is in the ring. That's why this element, it is an element in the ring. Yeah. So be careful that again I'll repeat, n is not an element, but I'm making into that that map will tell you, right? Yeah, it is now r into 1 again by that definition, and s into 1, right? Yeah, it is equal to 0, right? So by now integral domain, so this implies that either r dot 1 is equal to 0 or s dot 1 is equal to 0, right? So that is a contradiction, right? We got the required contradiction. Why we got the contradiction? Because n is the smallest positive integer, like that. But now I got r less than n satisfying that, right? So this part is done. So characteristic of an integral domain is prime if it is non-zero. So then automatically fields also that will work, right? Now we came to know that, yeah. So then as a corollary, the characteristic of finite field is, what do you say?
Prime number.
Prime. So there is no doubt in it, right? Why it is a prime first? So for that we need to sufficient to show that it is not zero, right? Again, proof, we need to give proof, okay? So we need to show it is non-zero. How do you it is non-zero? Since it is a finite field, it has a finite number of elements, and the field is a group with respect to addition. So if I add any element n times, what is going to happen? Zero. By which property? Which result?
Can you repeat what you said?
Okay. So why I am asking now, why characteristic of a finite field is not zero? See, characteristic of integral domain, we proved either zero or prime, right? Now, in order to say the statement is true, I want to show that characteristic of finite field is not zero, right? There is an integer n such that n into a equal to 0 होना चाहिए पहले. Yeah, out of them smallest is n characteristic. But if you're able to produce an m such that m into small m for Mumbai, m into a equal to 0 for every a, then there is an m, there is a positive integer m. Then out of them, I'll take the smallest by well-ordered principle. That is a characteristic. But I'm claiming there exists an m. How do you prove it?
So if there is no such m, then k times 1 will be non-zero for any integer k.
Right. But instead, I'm going in another way. What is that I told is, what is that I told instead of contradiction? Since it is a finite field, it has a finite number of elements. Then it has a cardinality, say m. Now m will take care. Why m into a equal to 0? That is the question I asked. Where m is the order of f. Yeah.
So we can pick 1 and then multiply it with, so we can take
Add.
So we take 1, 1 plus 1, 1 plus 1 plus 1. So all these are m distinct numbers. So one of them has to be
No,
0.
that much, that is okay, but yeah, you are correct. What is that I want to say, that n into 1 equal to 0. That's right.
Corollary to the Lagrange theorem.
Lagrange theorem. Yeah, that is what I do. Yes, exactly. Exactly as a corollary to the Lagrange theorem. In the finite field, so first of all, field is a group with respect to addition. So if order of f equal to n, then with respect to addition, order means how many times I add, it becomes 0. But by Lagrange theorem, order of every element is divisible by divides n, right? That is n into a equal to 0 for every n. So in particular, n into 1 is also 0. Yeah, field contains at least two elements, 0 and 1. Yeah. So we have prime. Yeah. I'm telling each and every part. So you go to interview, you say this again, we need to give the answer. Yeah. Okay. Yeah. Any questions? Okay. Good. So characteristic of finite field is a prime number. Very good. Yeah. So now I'm taking one after the another. Everything is very sequential. You do not feel that. See, some people will tell first one thing, result other thing, like. But I'll tell in a such a way that there is a flow for each and everything. Yeah. Let us go one after the another. So I'm telling this is now with us, right? What is the Tamiya saying, that also we'll use in a while. Yeah. So okay, at least since Tamiya told something, so I will use now itself. Okay. So for example, let f be a finite field. Let f be a finite field, right? Then it has a it has a characteristic. Suppose characteristic of f equal to p, right? So then you know that p is a prime number. Yeah. Then what is this telling? So I take 1, right? 1 belong to f. Since every field contains 0 and 1, they are distinct. Every field has at least two elements. Yeah. In the definition of a field itself, people say, yeah, 1, 1 plus 1, 1 plus 1 plus 1, right? Like that I'll go, right? So then how long I can go? They'll start repeating. Sorry. Yeah. Yes, please. I'll go up to p minus 1, right? When I touch p, I add the 1 p times, what happens? It becomes 0, correct? Then again I add, then it becomes 1. So they are going to repeat. Now if I collect this, my some set, okay, my s is equal to, so 1, 1 plus 1, right? 1 plus 1 plus 1, right? Up to 1 plus 1 plus. So I'm adding 0 also here, and 1 p minus 1 times, right? Right? Yeah. So then what we can say about this set?
The subfield of f.
It is a field. It is actually, this set is actually, it is becomes a field. So this field contains another field inside. So this is, so how many elements are there? First look at cardinality of s equal to p. Okay. So if you allow me, then just I'll write 2, 3 like that. Okay. Because I don't know what are elements. So, but so since we know that a field with p elements, so and up to isomorphism I can take, right? So that's why I'm telling this up to p minus 1, right? So do you know what is this isomorphic to? Equal to
F
z2,
subscript.
right? Z2, right? So what is that I want to claim is that if F is a field, finite field with characteristic P, then it contains inside one field, that is ZP. ZP is inside. As it is ZP, isomorphic copy of ZP, but people little lose it, so they will say that F contains ZP. Now also we'll use that. Is this part clear? Yeah. Okay. So I'll repeat once. F is a finite field, right? Then keep adding one several times up to p minus 1 times, including 0. So this is a subset of F clearly, and cardinality of S equal to P, and it is a field. Okay. What is order of 1 in F? In F, additive order. What is
P.
additive order? P, right? Yeah. Additive order of 1 is P. Because every element order is P. Because it is characteristic is P. So that is interesting. But how far you understand, I will check after a while. Because now I ask, you may tell. But really understood or not, I will ask after a while. So, right. Okay. So what is finally we done? So let F be if F is a finite field. Now what is that we done? I'm right. If F is a finite field with characteristic P, then ZP contained in F. Okay. That means ZP is a subfield of F. ZP is a subfield of F. It is also automatically says that people write like this. Another way to say is that F is an extension of ZP, right? Yeah. Now, naturally, question comes. I'll give various proofs now, but I'll little digress. Otherwise, you will tell answer immediately from this, right? Then you will not understand what exactly going. That's why I'll not tell. I'll now state some other result, and I'll get back to this, even though these are natural. Yeah. So I'm proving some result. Let F be a finite field. Then this F minus 0 with respect to multiplication is, it is one thing. Already it is abelian group. Can you say more?
Cyclic.
Is it
Cyclic.
cyclic group? That is one of the beautiful part. F plus dot is a finite field. In the finite field, if I remove 0 with respect to multiplication, it is a cyclic group. Is it true for real numbers? Rational numbers, complex numbers? No. Okay. So even though they are fields, right? Why this is interesting? For every field, it is not true. R minus 0, right? It is a abelian group, but it is not a field. It is not a cyclic group, right? Even rationals are complex numbers, right? But whereas finite fields, it is true. Yeah, how to prove that? Yeah. So this is the one of the question today first. Okay. So, but this can be proved with several proofs. That is what in my mail I mentioned. I need some results from the group theory. Yeah. Okay, I'll go one after the another. So question number 1. Okay. So question number 1. So let G be an abelian group, because I already know it is a abelian group, right? That's why I'm just confining to abelian group. group G1 comma G2 belong to G with order of G1 is equal to N1, order of G2 is equal to N2, right? Where N1 comma N2 GCD is equal to 1, right? Yeah, can you complete what is that I want to say?
Order of G1, G2 equal to N1, N2.
Yeah. So then order of G1, G2 is equal to N1 into N2. This is beautiful part for the abelian groups, right? So if their GCD is 1, then there is an element of order N1, N2 also. That is actually want to say. If you have two elements whose orders are N1 and N2, the GCD is 1, then I can find an element whose order is equal to product of these orders. That is one of the nice result. Yeah, how to prove it, right? Proof is very simple for this, right? For that, first let me take something. Let order of G1, G2 is equal to N, right? My claim is, so you know, the claim is N is equal to N1 into N2. Yeah. So is it all of you are clear, or I'm going fast, or you need some time? Let me know. Can I take a small break? You want that? After completion of this, I will take. Okay. Okay. So N is equal to N1 and N2, right? So what is happening now? So I will take G1, G2 power N, correct? G1, G2 power N1, N2 I will take, right? So this is equal to, so G1 power N1, N2 because of the abelian property. And try to understand that it is not even required entire group is abelian. These G1, G2 abelian also will work. That is a beautiful part. Okay. This proof does not demand entire group is abelian. Okay. Yeah, that in future, if you, I'm just telling that. Yeah. And here, you know, so this is identity and identity. So it is equal to identity. So from that, what is the conclusion? So N1 into N2 is divisible by N. N divides N1 into N2. This is 1, correct? Now I want to show others direction, right? How do you prove that? So can somebody can come up? Okay. So what is that I do here is, so I know that 1 is equal to identity is equal to, I already know.
We can use that, I think, Bazoo's theorem also.
I'm sorry, I'm not completely audible. Okay, I'll tell actually. So G1 into G2, so this power N is equal to identity because order of G1, G2 is N, right? So in particular, I'll multiply with N1 also, still not a problem, right? So this is equal to G1 power N into N1, G2 power N into N1, right? But you know that this is equal to G1 power N1 power N into G2 power N Nn1, right? So what is that I'm getting? G2 power Nn1 is equal to identity. Yeah. So from that, what is it conclude? We can conclude this implies yes, N2 divides Nn1, correct? Right? See, all of them are number theory only. N2 divides Nn2. Now this implies what? Now you know.
N2 divides N.
Yeah, n2 divides n1. Why? Because of Euclid's lemma, right? Since we done number theory course, n2 comma n1 GCD is 1, right?
Divides n.
A divides BC, yeah, and yeah. So A divides BC, A comma B GCD equal to 1, then A divides C, right? So that we are using, correct? Yeah. So similarly we can prove n1 divides n. But again I'm using that n1 comma n2 GCD is 1, right? And n1 divides n, n2 divides n. So from these two, so I can show that n1 into n2 also divides n. This also we done in the number theory course, right? But these are useful. Without them, we cannot proceed. Number theory is a very powerful technique. It will give a lot of things. So I don't know in India why people are not introducing number theory as a foundations, so that group algebra becomes easy. People are not getting algebra properly because of these reasons. So they do not know why this is happening. So there is no logic. So simply a teacher says that GCD 1, so n2 divides, but or sometimes even they not say n2 divides n1 n2, n2 divides n as well as n2 divides n1. They will say, right? They themselves may not know. Anyhow, sorry for those things. So what is that I proved is, if there exist two elements with orders n1 and n2 respectively, and the GCD of n1 and n2 is 1, then we are directly proving that there exists an element in the group whose order equal to n1 and n2. Now I want to generalize this. Okay. Yeah. So you take a small break. So we'll start at 9:40, right? Then I'll continue again. But actual finite fields I'm not started. But now after that it becomes very easy, straightforward. Yeah, so I hope this part is clear to all of you, right? Right. So now let us see, right? What is my next question, right? So my next question is that this part I want to generalize. This particular thing I want to generalize. What is that? Let G be an abelian group. Let G be an abelian group, right? And order of G1 is equal to some m, and order of G2 is equal to n for some G1 comma G2 belong to G, right? Then what is that I want to claim? There exists an element G belong to G. Such that order of G is equal to LCM of M and N. Is it okay? Order of G is equal to LCM of M comma. Okay. So I take LCM of M and N, then there exists an element whose order equal to this. So this is actually we proved here, provided M comma and GCD is 1. Now I'm not putting that condition. Even you take any two elements whose order equal to M and N, there is an element whose order equal to LCM of M and N, right? This is question number 2. Okay. So let us say this is question number 1. So are you able to prove this at question number 2? Right. So I will try to do this, right? Okay. So proof, right? Let I took M and N, orders of G1 and G2, right? So I want to construct an element whose order equal to LCM of M comma N. Yeah. Of course, that G is very much related to G1, G2. but it is not a product of G1 into G2, right? It is something that I want to bring, right? So that is the idea overall. Before starting the proof, how will go, right? So I assume that this M is equal to P1 power K1, yeah, A1 I will write, P1 power A1, P2 power A2, okay, and the PR power AR, yeah. N is equal to, again, P1 power B1, P2 power P2, and so on, PR power BR. You will ask one question. So why you took the same primes? It is possible to choose, right? So with the possibility that AI can be 0, right? BI can be 0. Are you following that part? Any question here?
Understood, sir.
This is very easy, right? So see, some primes are here, some primes are not there. I'll add all of them so that all of them have same set of primes. I can assume that. That is not a problem, right? Yeah. So once we have this, right, then I'll, what is LCM? You know, right? What is LCM of M comma N? You know that part, right? What is that? You know, we denote LCM like this, right? So I write this.
P1 power max of A1 B1.
So P1 power maximum of A1 B1, right? Like that, PR power maximum of AR and BR, right? Then I don't know if A1 is maximum, it becomes A1. B1 is maximum, it becomes B1. But it is one of among them, right? So what is I do now? I'll define two numbers, okay? So L1 and L2, okay? How I define? So this is product of all. So here AI is greater than or equal to BI. Those I will take, right? And the PI power AI. Are you following this part? So maybe little loosely I wrote, but I hope you understand this. What is it I have to write here? BJ. See, for example, A1, A2, AR, all of them are greater than or equal to B1, B2, BR. Then what happens? A1 is greater than B1, A2 is greater than B2, AR is greater than BR. Then can you tell me what are L1, L2?
L1 is M.
L1 is M, correct? L2 is?
L2 is 1. 0. There are no such BIs.
Wonderful. There are no such PA, so it is 1. Correct, you are correct. What is happening in that case actually? What is the relation between M and N? What is the relation between M and N in that case? If A1 is greater than B1, greater than or equal to B1, A2 greater than or equal to B2, AR greater than or equal to BR, then what do you know about M and N?
N divides N.
N divides M. Then what is LCM?
M.
M. And am I proved there is an element of order M? Yes, correct. In that case, not a problem. So these are non-trivial when one of these BIJs is greater than 1, right? Just I am asking you to understand what is I constructed here. I am asked that question to make it clear to you that so things like this, right? So by definition, L1 is divides what? And L2 divides what? Do you see that? See, I am collecting only those primes A greater than BI.
1 divides N.
L1 divides
M.
M, right? L1 divides M and L2 divides
N.
N, right? Are there any primes common in these two? So
Yes, sir.
So greater than or equal to I wrote, so I do not write that way. Yeah, sorry. I'll remove this, okay? If I remove, then there is a problem, right? एक जगह पे तो equal हो सकता है, right? So I'll put one side equal to, other side greater than. Is it okay for you?
Yes, sir.
Yeah, right. Then what is going to happen now? Now what we can say about GCD of L1, L2?
One.
Hmm?
One.
1. So this proof is wonderful proof actually, very nice proof. Yeah. Right. So till now, no problems. This is only number theory, purely number theory. So we have this, both the numbers written as single set of primes, prime powers and maximum, and then I constructed this. One side I greater than or equal to, one side greater than. So their GCD is 1, right? So now what is going to happen? So I will take my G1 power, right? What is that I have to take? What is my element actually, whose order equal to, what is LCM of L1, L2? Yeah, can you tell me that?
Product.
LCM of L1, L2.
L1, L2.
L1, L2. Okay. Is it equal to LCM of Mn?
Yes.
Yeah, it is LCM of Mn, right? So now if I able to produce, there is an element of order L1 and L2, then I am done with the previous result. How do you get it? Can you predict that? You know that order of G1 equal to M, order of G2 equal to M. This much I know, right? Now can you construct an element whose order equal to L1 and whose order equal to L2?
And I think raise G1 to some power.
Yeah, so if I take G1 power L1, L1 or L2?
L2.
L2, let us see. Then power L1, if I do, what going to happen?
It will be LCM of Mn, which will be a multiple of M, so it will be 1.
Okay. So it is one identity, right?
Yes, sir.
So order of this is equal to L1. So order of G1 power L2 is L2, right? Yeah. So think about, I'll give some time to you. So if you have any questions, you can ask, right? I'm looking, so I'm just one modification here. I'm just recalling that actually. 1 minute. Because L1 divides N1, so I'll try to take up that and see. What is it I'm doing is that I take G1 power M by L1, right? So I take this element. Because L2 is not coming in the prime factors of M, right? That's why I'm just, let us look into this, okay? G2 power N by L2, right? So it is clearly an element of the group G. So this is my X, right? So now what is order of G power m by L1?
L1.
L1. This is L1. What is order of G power n by L2? L2.
L2.
Right? Then what is order of X? L1 into L2. Right? But right? So that is equal to LCM, right? Is it done?
Yes, sir.
Yeah, good, simple. Sorry for here small switch. Because L2 has not come into M, that's why I just start off this. Yeah. Any questions? What is the question? Actually, this is the main question, but this require this result, so I used that, right? This is easy. So now this we have. So we have two elements whose orders are M and N. Then there exists an element whose order equal to LCM of M and N. This G, of course, constructed from G1, G2. So these those G comes from G1 power N by L1, G2 power N by L2, right? That is what. That is the required element. Yeah. Now I'm coming to the another question. With that, we'll go to the our original question. Okay. This is the only thing I need. Okay. Because you need to have a logic in each everything. I cannot use so many things, right? You've done group theory very long back, so you may not recall. That is what happening in this course. Okay, this course demands a lot of previous things, right? So that's why, yeah. Anyhow, okay. So my question is this now. Question number 3. Let G be an abelian group. Let G be an abelian group, right? And M is maximum order. Okay, let G be a finite abelian group pilot so that the things will do much better. Sorry. M be the maximum order of elements of G. Then, so can you say something?
Order of any element must divide M.
So you know, right? Yeah. Order of G divides M for every G belong to G. This is actually my result actually. Till now, question 1, question 2, question 3. This is my original actual question, right? So this is beautiful part of the abelian groups. So out of all orders, maximum, that is called exponent. Sometime in the previous lectures, one of the time I defined it. Exponent of a group. Exponent of a group is the, so if G is a finite group, so we done it actually. G is a finite group. Then how exponent is defined? So let G be a finite group, right? So we collect all M natural numbers such that order of G is order of G divides, okay, or otherwise G power M equal to identity for every G. I'm collecting those natural numbers. G power M equal to E for every G belong to G. I'll recall GBA, I repeat, let G be an abelian group with respect to multiplication, right? Suppose I'm collecting those natural numbers, G power M equal to identity. Is it empty or non-empty?
It's non-empty.
Yeah, so order of the group is always be here. So it is non-empty. So by Vallarting principle, it has a least element that is called exponent of the group. But for abelian groups, we can tell that it is need not be order of the group. Yeah, abelian groups also cyclic. In that case, of course, it is order of the group. But we can go little lesser. Out of so this is a, so there is an element. If it is not cyclic, The m is the maximal order, right? So it is exponent is less than the order of the group. That is the beauty of this result. Okay. Any questions? It's complicated. So exponent of G is equal to the maximum order of the some element. Yeah. For example, S3, what is exponent? 6 only. What is the maximum order in S3? 3. But there are elements of order 2, does not divide it. So non-abelian group, this property is not true. Yeah. Yeah. So how to prove now this result, right? Any idea?
Can use the previous result.
Sorry?
You can use the previous result.
Right. So what is that you take? So instead of proving, this is true for every G I need to prove. So I take one particular element. Let G belong to G, right? So what is my claim? What is that I have to show? Order of G divides M, right? Yeah. But M is also order of some element. Okay. Since M is also order of some element. Say H. Right? M is the maximum order of elements of G. Out of all orders, maximum. So, but M is also order of some element. Okay. Now, what is the previous result says? There exists some K belong to G such that order of K equal to, yeah, order of K equal to LCM of, right? Please tell. Okay, let us say order of G equal to N, right? Yeah. Now, can you tell? I have two elements. One is order of G, that is N, and order of H equal to M. What is the previous result?
LCM
says?
of N, M.
LCM of M, N, right? Yeah. So, yeah, this is what we have, right? So now how do I prove that N divides M now by these two?
We show that LCM of M, N is equal to N.
Yeah, right. See, you know that LCM of Mn, LCM of M, N, right? And M. So clearly it is greater than or equal to. But what is the theorem it is given? M is greater than or equal to LCM. Because LCM now is an order of some element, right? But M is the maximum of all orders. So this implies M is equal to LCM of M, N. Right? Yeah. So this implies so N divides M. Any questions? Any one of you, please. I'm giving gaps, okay, so that we'll recall, revise. So if you are fine, can you tick yes? Okay. Or you let me know, right? Can you tick yes if you are fine with this proof? So very less number of students are there, it seems. Others are not following. Okay. Yeah, what we can do now? Okay. So those who are not followed, so assume this result is true. Huh? We'll proceed now. Okay. Please back now to the finite fields. What is the result I want to show? Remember, I asked 3 questions to prove something, right? This is the question. Now come back to this. Assume these results. Proofs are available, you can check later. Yeah, concentrate. So now I am telling that multiplicative group in the finite field is a cyclic group. That is my question, right? Yeah. So this is what I want to show, right? So here all the things are coming. Okay. So proof for that part. Let F be a finite field. See here, I do not need how many elements are there and all. Yeah. So of order Q, let us say of order Q. Later we prove that Q is actually prime power and all, but at this juncture I do not need that. Yeah, order Q. Yeah. So then what is order of this one? What is the cardinality of order actually? So this is equal to Q minus 1, right? Climb is it is cyclic. Climb is cyclic, right? This is cyclic. That means there exist, right? So G belong to F minus 0 such that G power order of G equal to Q minus 1, right? Order of G divides Q minus 1 is very much clear, but we need to prove that, right? So what is the strategy? So again, I'll take let M be the maximum of order of G so that G belong to F minus 0. Is it okay? This set is okay. What is M now? Maximum order element in the group F minus 0. Right? Out of all orders, this is the maximum, right? Okay. Good. Okay. So then what do we know from previous result?
Order of any element must divide M.
We know that order of G divides M for every G belong to F minus 0. So what is that meaning again? That means that if order of G divides them, then what about G power M? Yeah.
Equal to identity.
Equal to 1, right? Equal to 1. So this is true for
All G.
all G. For every G belong to F minus 0, right? We have G power M is equal to 1, right? Okay, by the way, what is the relation between M and Q minus 1?
Less than equal to.
Less than or equal to, or even divides also, right? We know that order of
Yes,
any
sir.
divides the order of the group. This is order of the group. So this we have, but less than or equal to is okay. Yeah. So so from this also we can show less than or equal to, right? Now what next? Yeah. So since Amya is ready, so you can tell, no problem. Yeah. Now tell me, how do you now prove Q minus 1 is less than or equal to M?
So we look at the polynomial x power m minus 1.
Yeah. So from this, what is the conclusion? So every element of F minus 0, okay, satisfying x power m minus 1 is equal to 0. Yeah. Right? Satisfying the polynomial, right? Satisfying the polynomial. X power m minus 1. But we know that that means all the, so then what we can say? But we know that in a field, how many maximum roots will be there? Number of roots of this polynomial of degree m is
Most
less
q
than or
minus
equal.
1.
Yeah, but
At most
all
q
these
minus 1.
elements are satisfying. So what is the relation between q minus 1 and m now? These are all the roots, and m is the degree of the polynomial. And we know that in a field, if I have a polynomial of degree m, it has m roots. But all these q minus 1 are roots now. So what is the relation between q minus 1 and m?
Less than equal to.
Less than or equal, right? So I have m equal to q minus 1. What is that I proved? So that means implies there exists an element there exists an element G belong to F minus 0 such that order of G equal to M. So that is equal to Q minus 1, right? So G is, so F minus 0 is cyclic. Is the proof is clear?
Yes, sir.
Yeah. Wonderful. This is what we need. Okay. So this part is okay. So when somebody else can say everything fine, can you open up and unmute and say, is this proof is okay?
Yes, sir, it is okay.
Yeah, good, nice. Yeah, very good, wonderful. Yeah. Now, this is a beautiful part. So if let F be a finite field, implies order of F equal to P power n for some prime P and natural number n belongs to n. Okay, is the statement is clear? Cool. So don't worry. Again, come back. Concentrate now onwards also. Wonderful. No problem. Forget about previous part. So some of you are clear with up to characteristic, right? I came to group theory. You may be, some of you may be lost, but don't worry. That you can recall later. Yeah. You can also mail me. You can write to me. So do not hesitate to write to me. So I have not understood. Can you spare time? I'm ready to spare time. Please write to me. Yeah? Whenever both of us find some free time, we can meet and again discuss. Not only for this, previous classes also. My goal is that every one of you has to understand, right? So at the class time you do not understand, you not attended, still fine. Write a mail to me. So please free. I will explain from the very basics. You can ask any question. Yeah. Right. Okay. So now coming to this. So question coming, right? So I have let F be a finite field. From where this P comes first. From where this P comes from. I'm writing so that in future also you look at these notes from where this P comes. I asked questions naturally to me from where this P comes. Yeah. So can you answer to that?
Characteristic.
Yeah, correct. Yeah, so simple, right? So from the characteristic. Yes. So first prime, I need to bring prime as well as n, right? First I brought the P. How I got? Because we proved that in a finite field, characteristic of finite field is P, right? So I got P. So which P? That is exactly the characteristic. Okay. So this part is done. So that part is done. So every finite field has some characteristic prime P. So that is the P, I use it. Yeah. So that part is done. Now how to bring n? Right. Now question number 2. Right here. So question 1 is done. Question 2. How do you, from where will get? Right. I will give 2 different proofs for it. Yeah. Anyhow. So first this one. Right. Yeah. Anyone? Okay. See. So F is a finite field. See, this is the reason I told at that time, I do not, if I ask answer, immediately you will tell, right? If I give a break, then you may not tell. Yeah, this is the point. if F is a finite field with characteristic P, with characteristic of F equal to P, yeah, then what is that you know? F contains, yeah. Now can you recall? F contains ZP, right? So if it contains ZP, then F is extension. F is an extension of ZP, correct? Good. If it is an extension of ZP, then what happens? We can talk about, so I'll tell actually. So if F is an extension of ZP implies F is a, yeah, can you say something?
Vector space over ZP.
Vector space over ZP. If it is a vector space over ZP, then what happens? This implies, so there exists a basis of F over ZP. Yeah, is it finite?
Yes, sir.
Yeah, it is finite. Why it is finite?
The field
Because
itself is
it is
finite.
finite, right? If F itself is finite, how basis can be infinite, right? So we have a finite basis, right? Okay, suppose that from there this n coming, that is the place, okay? So let me write that so that you will clear later, right? So that is the place n comes. Yeah. So in a movie, hero enters now at some stage. Heroine enters some stage. So hero P entered in the very beginning. Yeah. So now heroine N entered. Yeah. So it entered as a number of elements in the basis. Yeah, there exists a basis of X over ZP so that it is finite. Yeah. So how many of you watched Pushpa? Okay. Yeah. Right. Okay. So N comes, right? So let now let us assume that this V1, V2, oh, you may not happy because there are elements in the field. So why you are writing like vectors? Okay, I'll write. How do you write? Okay, so A1 comma A2 comma AN be basis. Okay, let us write some alpha one. V1, V2 I'll write. Okay, don't think of vectors. Okay, convenient actually. Later when be a basis of F over ZP, right? Good. Now what is how P power n? Now combination is coming. Yeah. Yeah. So how combination is coming? How song between hero and heroine comes, right? How combination is coming. Yeah. That comes like this, right? I take let X belong to F. Field F. Now this is the basis. So what happens? X is equal to, it is in the linear span, right? So X is equal to, so there exists n first. So what is the meaning? This implies that there exists n belongs to natural number such that first thing is this basis linear span is this. It is a linear combination of finite linear combination. So that's first thing comes is that there is some m, but already this is finite, so I do not worry about that. So are you following? If the basis is infinite, then there is a finite I'll take, but here already basis is finite. Directly I can take there exists a1 comma a2 comma a n belong to ZP, so is it X equal to a1 v1 plus a2 v2 plus and so on plus an vn. Is it okay? So how many choices are there for A1? Yeah, anyone? Am I audible? Am I audible?
Set P number of choices.
P choices are there because this A1 can be 0 or whatever, P choices. So here I have P choices, here I have P choices, here I have P choices, right? When you look at the nodes, the sticks are that I told that there are P choices for A1, P choices for A2 and so on, P choices for AN. That many distinct elements will be there. So the cardinality of F equal to P power. Yeah. Yeah, so this is by field extension. F is a field extension over ZP. So there is a finite basis based on that. So if you understand the proof, it's okay. Those who do not understand, don't worry, I'll give another proof. Okay, by using group theory now. Okay, now I'm giving the proof by using group theory. So question number 2, not question number 2. So proof by using group theory. Okay, but so P again came from the characteristic only, N only I'm talking about. Yeah, so let F be a finite field. Let me write a new page pane, huh? So that it will be what is that actually I'm doing, it will be clear to you. Correct? Yeah. So what is my question? So let F be a finite field of characteristic P. So claim there exists an n belong to n such that order of F equal to P power. This is the goal, right? So that means that order of F is prime power, that prime power only. So that is what is that I have to show. That is if Q is any prime, and Q not equal to P, then can you say something? See, if order of F is not P power n means what? It is equal to some other Q is also dividing, right? Then Q divides order of Q. Are you following this part, please?
No, sir.
See, if I able to prove that order of F, if we are able to prove that, since you are not understand, I'm right.
But we already proved
What we proved?
that there are like n choices for AI.
No, that is I done. What is, yeah, so you are not here. See, this is one proof I done. Proof is over. Order of F equal to P power n is done. In this proof, I used the extension of the fields, right? Field extension, right? I'm giving alternate proof now. Are you okay, Amya?
Okay, sir.
I'm giving now a different proof. Why order of F equal to P power n? But P comes from characteristic only. That n, in the previous proof, n came from the basis. And field extension is there. But so those people who do not done the field extensions, there is a way. Yeah, I'm giving that. Is it okay, Amir?
Okay, sir.
Yeah. So what is that I want to say? So order of F not divisible by any prime Q. Okay. So then what is going to happen? Okay, I'm writing here so that it will be clear to you. I'm telling if Q is any prime, then Q not equal to P, then Q does not divide order of F. For example, if I prove this, what is the meaning of that? This implies what? Yeah, I'll ask further questions. It is a finite field, and you know that order of F is greater than or equal to 2. Why it is greater than or equal to 2? You know that at least 2 elements will be there. So that means cardinality of F equal to some prime, it's some number, right? But I'm claiming that is equal to prime power n only. For that, I assume that it is equal to p power n only, right? So is it sufficient to prove that, to show this one, is it sufficient to this? If Q is any prime, Q not equal to P, then Q does not divide order of F. This implies order of F equal to P power n only, I'm claiming. Is it correct or not correct? There is no other prime is dividing, right? Only prime dividing order of F is, hello? At least one person. Otherwise, I'll not do. No need to do this proof also. Is it okay or not okay? Now time is coming. I need to ask one person at least now. It is because whether you are following it or not, right? Yeah, Amaya. Okay. Anyhow, I'll complete then. Yeah. So what is it? I want to say that, for example, there is a prime Q. Q also divides order of F, right? Okay. If Q divides order of F implies right? So implies, so now I'm taking that F is an abelian group, right? F plus is an abelian group. Yeah, and is there exist, so yeah, Q divides implies order of there exist an X belong to F such that order of X equal to P, Q. Do you understand that? Do you know why this is? Q divides order of a group, then there exists an X belong to such that order of X equal to Q. Do you know this?
Cauchy's theorem.
Cauchy's theorem. Yeah. This is one result I'm using. There I'm using field extensions. Here I'm using this much only. If a prime divides order of the group, then there exists an element of that order. Right? Yeah. So that means that so Q dot X equal to 0. But what is P dot X equal to? X is an element in the field. This is X plus P times, right? What is this equal to? F is a field of characteristic P. Yeah. What is this equal to? Okay, no one want to respond. So it is 0, right? So then what happens? So this implies, but what about Q comma P GCD? That is 1 because Q is different from P I'm choosing, right? This implies there exists some M comma N belong to integers such that my QM plus Pn is equal to 1, correct? Yeah. So this implies, so 1 into X equal to, so Qm plus Pn into X, right? So this is equal to 0. That means X equal to 0. So this is a contradiction. is the contradiction as order of x equal to q. This comes from so q does not divide order of x. So q does not divide order of x. So only prime divisor of f, order of f is, yeah, can you say now? Only prime divisor of order of f is p. Yeah, I think you are not following, but anyhow. So this is the thing, right? I proved in a different way by using Cauchy's theorem of the group theory. If you're not happy, you can leave it. So we done it actually. I will start with one last question, right? One last question. So let f plus dot be a finite field, right? See, today just I proved that finite field contains p power n elements, but if there is a finite field, then it has to order is p power n. But I'm not proved that for every p, every n, there is a finite field. That we will do in the next class. Okay, I'm telling you that next class, what is that I'm going to do? Be a finite field. What we can say about this group? Is it cyclic? You know that f minus 0 is cyclic, right? People will confuse. Okay, so generally they say that then f plus is also cyclic. They remember and they will say something is cyclic, so f plus is also cyclic. What do you know about f plus? This is cyclic on one case. If my order of f equal to p, prime number itself, okay, then both f plus and f minus 0, both are cyclic. Yeah. Otherwise, what?
It's not cyclic.
Not cyclic. So, but it is isomorphic to what? If order of f equal to p power n, where n is greater than or equal to 2, then f is isomorphic to what? Can you say that? Okay.
I mean, we can like quotient it with some polynomial.
No, not that way. See, simple things only I'm asking. Yeah. Yeah, luckily you do not, no one asked this question to you, so very good. So I asked today at least. See, what is, if I take any element in F, okay, if I add p times 1, what happens?
0.
0. Then what we can say about order of x?
And order of what?
Yeah, okay, fine. See, my point is that order of an element, order of f equal to p power n. Then order of an element is a divisor of p power n. Right? Additive order. Now additive order.
Yes, sir. Yes, sir.
Right? So then what is the possible order of an element now? If it is 0, then order is 1. If it is non-zero, then
P.
p, exactly p. So very wonderful thing is that every element, order of every element is p only. Every non-zero element order is p only. So it is isomorphic to zp cross zp cross zp. Are you following that?
As groups, right?
Yeah, as a group, yes.
Okay.
As a group. So see, that is a thing. So as an abelian group, it is isomorphic. As a cyclic group, it is isomorphic to z p power n minus 1. Are you following that?
Yes, sir.
So beautiful structure, two different structures. Yeah, it is called elementary abelian group. Elementary abelian p group. Yeah. So actually in the interviews, so many times we'll ask, but people not tell. That's why just trying to recall connect. Okay, then I'll stop here. Thanks.